That is the experiment that we are actually planning to do in our next class period. Simple pendulum. So first of all, what is a simple pendulum? And what is a pendulum? First of all, let's discuss what is pendulum.
Swings back and forth.
Yep, something that swings back and forth. Here is a pendulum. Essentially, it contains a string and what is known as a bob. So what is here? It could be a heavy object. Anything that's heavy and small can be a good bob. Okay? So this is basically a pendulum. A string connected to a bob. That is a pendulum. Now, the word simple means it is not complex or complicated. Simple simply means not complicated. So what do you mean by a complicated pendulum? Here is one example of a complicated pendulum. Well, this is a conical pendulum. This is a conical pendulum. It is complex. Now, why do you say it's complex? Because to determine where the bob is at a particular time, it is much harder. Mathematically, to get it, it's harder. And that's why it is more complex. Okay? Now, imagine I have one pendulum. This is not, it's made of a rubber band. Imagine it's made of rubber band, and if I swing it, how do you think it is going to swing?
Jumpy.
It'll be like, right? It'll stretch and compress, and that'll be complicated. So it's that sort of pendulum, to decide, to find out where the bob is at a particular time is going to be very complicated. Or worse still, imagine there are two pendulums. One is here, and there is another pendulum connected to the bottom of this. So there are basically two pendulums connected, one one under the other, or three pendulums. And if you swing it together, do you think it will just go together like this?
No, it's going to go, like the bottom one's going to go in a circle.
I mean, they both will have their own timing, and so it will be a kind of awkward oscillation like this. Imagine this is the pendulum. This is the first suspension, and this is the bob. Another suspension, and this is another bob. And if I swing it, it's not going to swing like this. Instead, probably it's going to swing like, you know what I'm saying? That sort of.
What about the one at like the side towards
The big one?
Yeah.
Which
So it
that's
knocks down the
That's almost a simple pendulum, but actually it's moving from, changing the angles because of the spin of the earth and all that. So that's why it's knocking off little by little. So yeah, you understand the word simple now. Simple pendulum simply means like it is a pendulum that goes only in one simple plane. Okay, that is a simple pendulum. So here is a simple pendulum. There it is. That's a pendulum. What is special about this pendulum is when it is swinging from side to side, it maintains a rhythm or timing. It maintains a time period. So the time period is actually given by the equation 2 pi radical L over G. That is the actual equation for the time period. You don't have to know how it is derived, but right now we are using that equation. Time period is 2 pi radical L over G. So time period, which means what? How long it takes to swing once. So T stands for time period, which is the time taken for one complete oscillation. One complete oscillation. How long it takes for one complete oscillation, that is called time period. And if you watch this, you can see the time period. How long it takes to swing once. And when I say once, start from here and end here. That's once. Or better still is to start from the middle. Start from the middle, go like this, that completes one. right? Start from here, return back to the same spot where it started. That is called one oscillation. So time period is the time taken for one complete oscillation. And what do you see the time period depends on? Length. And the bigger the length, what should happen to the time period?
Should get longer.
Longer. Shorter the length? Shorter the length. See, look at this timing. Shorter pendulum. Right? This is a shorter pendulum. And it is shorter time. The time period depends on the length very much. So time period is dependent on the length directly. Now the other one is gravity. This is the acceleration due to gravity, which is here, 9.81, right? On the moon, gravity is only 1/6, which is very small. So when the gravity is small, what will happen to the time period? Longer. So on the moon, this pendulum is going to go like this. On the moon. It's going to have an extended time. Is that clear? So time period depends on this. Does it depend on the mass of the bob? No, it does not depend on the mass of the bob. So the bob needs to be heavy, and it can't be a ping pong ball, because the ping pong ball will suffer a lot of air resistance, or it will struggle to continue oscillating because of air resistance, whereas a steel ball or a lead ball will actually, because it's heavy enough, it will be able to fight air resistance and maintain the oscillation for longer. Get it? So mass is not coming into the picture. So this equation can be applied everywhere. Like, imagine you go to a park. You go to a park and you see a swing. And you sit and swing. Now, there is an identical swing of the same length. That will also have the same time period. So both can go together. However, if the next one is actually shorter, that will go faster. And if the next one is longer, it will take more time. Right? The swinging. Have you been on the swing? Okay. So you go to the park, you swing on the swing, and then after some time you get bored, and then you stand on the swing. Have you done that too? Standing and swinging? Oh, what do you think is going to happen to the time period if you stand and swing? Is it going to be the same or different? It's going to take longer? Or shorter? Or stay the same? See, you sat on the swing, and after some time you're standing on the same swing. Huh? So
It's faster.
it is faster. In other words, less time period. So what does that mean? That means the length of the pendulum, L, is the effective length, which is from here to the center of gravity of the bob. So it is not from there to the bottom of the bob. That's why when you stand on the swing, your center of gravity is higher, which means the length of the pendulum is actually effectively reduced. And when the length of the pendulum is reduced, you will be going faster. In other words, less time period. You might not have noticed it, but try it next time. Go and stop with the stopwatch and do the same thing. Swing, complete 10 oscillations, and then stop, and then stand and do the same thing, and you'll see a clear difference between standing and sitting. Okay? The standing will be faster. Sitting will be slower. So that's what the equation actually tells you about. Those are things like that. Even our human leg is a pendulum. Our leg is a pendulum. So it is suspended here. The pendulum is suspended here. And our leg is, so our natural walk. What is a natural walk? See, you're kind of leaning forward, and what are you doing to the right leg? Just letting it go. And what does it do? It swings to the next spot. And the next one swings to the next spot. How much time does it take for the leg to swing? depends on the length of the pendulum. So how much is the length of my pendulum, the leg?
Probably like 3 feet, something like that.
Yeah, so from where to where do we measure?
Hip to the bottom of your
To the,
Your knee.
is it to my feet? No, it is to the center of gravity of my leg. Where is the center? Okay, it is suspended here. The center of gravity of my leg is kind of above the knee.
Because your thighs are
Exactly. My
Right, yeah.
thighs are bigger, feet is smaller. And so the center of gravity is probably closer to, like it is above the knee somewhere. So that is the length, which almost is, it's kind of this much. So this is my frequency of walking. This is how I walk, like that sort of frequency. So everyone walks according to a certain timing, and that timing is decided by the pendulum that we have. I'm talking about a casual walk, where you can walk for miles and not get tired.
So like when a midget walks, they're like Mr. Krabs.
Hmm?
Like
Yeah.
It's kind of offensive.
I mean, it's a fact, Okay, so tall basketball players, you know how they walk? Or they walk in a lazy fashion. Have you noticed it?
yeah.
They walk like tall basketball players. They walk a lazy fashion. We almost look at them and say, he's lazy.
That's what Mike tried to do.
Why he is appearing to be lazy is because it's not his fault. It's just his timing. If the leg is swinging, taking more time. Whereas look at some other people, like, look at Mr. Budniak, for example. I'm just giving.
He walks very fast.
Huh?
He just walks fast, though. Like,
No. It is just because the shortness of the legs.
No, but like, he does walk pretty fast.
He does.
Like,
It is not.
He talks fast too.
yeah, he does.
All right. We're not going anywhere else. I'm just comparing him because he's got shorter legs, so naturally he will be swinging his legs faster. Yeah. I mean, that's how.
He has
That's,
a little walk, like,
no, you just look at somebody and then see how they walk. They'll be like, like quick steps. And the quick steps is not because of the fact that they are brisk or because they are deliberately trying to do a brisk walk. It is their natural walk. Little kids will be walking like, it'll look like they're running. But that is their natural timing. Taller people, more timing. And it all depends on what? The effective length. L stands for effective length. L stands for the effective length, which is from the point of suspension. Now imagine somebody has a leg like this, that shape.
Where's the knee?
Okay, got it. If somebody's leg is like this,
That's Saquon.
the center of gravity is pretty high up here,
Draw his kneecap.
which means what? They will be walking fast too. I mean, you try to look at some people and look at the structure of the leg, and you can almost figure out how fast they'll be walking. Really? So it's all physics, completely. Okay? Good. All right. So, what are we trying to do in the lab? What is our goal? Our goal in the lab, our aim in the lab is to determine the acceleration due to gravity by using this simple pendulum experiment. So our goal is to find out, the aim of the experiment is to find the acceleration due to gravity in the lab by setting up a pendulum.
So find acceleration of pendulum.
No, acceleration due to gravity.
Oh,
The G.
yeah.
That's what you're trying to find out in the lab. How? By investigating length and time to determine the acceleration due to gravity.
On the pendulum in the lab.
No pendulums and all that. To determine the acceleration due to gravity in the lab. Finished. We're using a pendulum as a tool. We can use so many other tools to get that same thing done.
What was the how? What was the how? You said how? You said you go how?
Oh.
Yeah.
We are doing it with the pendulum, with the help of a pendulum. Oh.
You said
So
investigating.
by investigating the oscillations of a pendulum. All right, so the aim of the experiment is to determine the acceleration due to gravity in the lab by investigating the length and time period of a simple pendulum. All right, is that okay? Now, what are the materials you need? Probably you need a stand to suspend the pendulum. We need a string. We need a bob. We need a meter stick to measure the lengths. We need a stopwatch, which is basically what we are going to use. So we're going to use cell phones for the stopwatch. So, stopwatch, and that's pretty much it. We don't need anything else for this experiment. Now, if you're going to do this at home, you can still do it. I have made students do it for snow assignment. I made them do it for snow assignment, which is what? Find a lock or something like that, which is heavy, and find a string. And then
Necklace.
A measuring tape. Okay, the measuring tape might give you in inches, but you can always convert it to meters, right? And that's it. And then your cell phone is your stopwatch, and you can actually do the experiment at home. I have had some students say, "No, I don't have a string at home." I said, look for something that can work as a string. Do you have a piece of electrical wire, extension cord? What is that? Something as a string. Yeah, sometimes students always give excuses saying, I don't have this, I don't have that, and all that. You can always get it. If you just look for it, you'll find a string, you'll find something or the other. And or you can use your own tie or whatever, something like this. Or your lanyard.
That's good.
Yeah. So like this. So all we need is to investigate. We need to set up a pendulum. All right. So I went through the aim. I went through the materials required. What comes next? Theory. And I already talked to you about the theory. What's the theory of a pendulum? When a pendulum swings back and forth, it maintains a time period, which is given by this equation. And then you can say the larger the length, the more the time period, the larger the g, the shorter the time period. Those are kind of the theory part of it. And first of all, why does the pendulum move back and forth? Why does it swing? Why does it keep swinging like this? What exactly is going on? And you should be able to say that because we have had the background information in a couple of days. What kind of energy is being transferred from here? And what is the energy here? Kinetic. And then it goes back to? And then back to kinetic, back to potential, and this goes on. And of course there's a loss of energy. That's why it actually comes down, right? It loses energy. Slowly, it will come down. But how quickly it comes down depends on the mass of the bob. So the mass of the bob is like, if it's a steel bob, heavy and small, does not have much wind resistance thing, then of course it will keep going for a long time. Long time. Yeah.
So it slows it down. Right?
Air resistance. Yeah. That's why I said, instead of this key.
But if it's in like a gravity-less,
Gravity-less place?
like a
Gravity.
place without gravity.
He means back.
There's no place without gravity. The gravity is always there. The only thing is in space you can have an apparent gravity of zero. You can feel as if there's no gravity. That is a feeling, but gravity is always there.
What if you're like flying in a plane and then they go really high and you go like dive bomb?
That's apparent G. The apparent G can be zero. Now, what happens if the apparent G is when this is zero? What will happen? When you divide something with zero, what do you get? Huh? When you divide something with zero,
Undefined.
It becomes zero.
You can't divide.
No.
I'll show you how to. Okay, I'll teach you some division now. Okay, I've got a basket. I've got 100 apples in a basket. I'm going to divide it among many people. Okay, so if I divide it by 50, like I take 50 at a time and distribute it, how many people can I distribute it to? That's because 100 divided by 50 is 2. If I take 10 apples at a time and distribute it, how many people can I distribute it to? 10. If I take 1 apple at a time, how many people?
100.
So 100 divided by 1 is 100. If I take half an apple at a time, how many people can I?
200.
200. If I take 0.1 of an apple at a time, like 1/10 of an apple, how many people? 1,000 people I can serve. If I take 0.01 of an apple at a time, how many people can I serve?
So if you take 0 of an apple,
10,000
infinite.
people. So if I keep reducing the amount of apples I take, how many people can I distribute? That number keeps going.
Infinite.
So if I take 0 apples at a time and distribute it,
Infinite.
I give 0 to you, I give 0 to you. How many people can I distribute it to?
Infinite.
Infinite is the answer.
But nobody got any apples.
No.
Yeah.
That's not a point, Preston.
That is the point. So when you divide anything with 0, the answer is infinite, not error and stuff like that. Infinite is the answer. So when you have 0, a parent G is 0, you're dividing something with 0, the answer is supposed to be infinite. So what is supposed to be the time period? Infinite. Which means what? It'll take forever. So if I take this thing
Perpetual
in a
life.
space station and then release it from here, it'll stay there.
It'll never stop.
No, it will
No,
stay
it'll
here.
never
It won't
stop.
even move.
Dave, are you
If I leave it here, it will stay there. In a space station, if I leave it like this thing is not going to come down. It's going to stay there.
What
Which
if you-
means how long will it take to complete one oscillation? Infinite time. Make sense? That means it'll take forever. That's what it means. Yeah, G. All right, coming back to the theory behind this experiment. So you have to just say potential energy, kinetic energy, potential energy, kinetic energy changes, and that is what keeps this pendulum going back and forth. But as it is moving back and forth, it maintains a certain timing, and that timing is given by this equation 2 pi radical L over G. Is that clear? What comes next after that is the formula used. You can write the formula used here, and you will see more formula as we go on.
There's multiple formulas.
Because we are not going to use this formula straight away. Because we need to investigate and find G. Let's find out how much is G. How do I get the square root out of this equation? How do I get rid of the square root? Square both sides. So if I square both sides, I get t square is equals to 4 pi square, because 2 square is 4, pi square is pi square, and L over G. And if you cross multiply this equation, you get gt square is equals to 4 pi square L. This is gt square. So what is G? It's 4 pi square L over. This is your equation. Well, this equation is not easy to use, but you are trying to find out what? G, right? I made G the subject of the equation. So this is an important equation. And we are trying to find out G. By investigating what? By investigating the length and time. Length and time. How much length? How much time it takes to swing. So this is the formula used. I'll give you one more step of the formula later. Okay, what do you do next? Procedure. So whatever you do in the lab will be a procedure. Okay, write it down in a bullet form. And what comes after procedure is observation. Observation of what? Observation of your investigation. So what are we trying to investigate? Length, and we're trying to find out what? Time period. So now let me plot let me show you what table you're going to use. The first column is length and is measured in meters. The first column is length. So for example, if I suspended the pendulum and if I used a meter stick to measure the length of the pendulum, actually I'll see where the center of gravity is. And if I find that the center of gravity is at 30.7 centimeters, is how many meters?
3.307.
Yeah, that's what you write. This is just an example. You don't have to use this number. All right? So this is probably the length. And the next column is for time of 10 oscillations. And again, it's measured in seconds. Time for 10 oscillations. Why 10 oscillations? Because when you're swinging it like this, when you take the time period, if you start from here and end here, it's kind of fast, and so you may make more errors with your starting and stopping. So you can have plenty of errors. To minimize those errors, we do it for 10 oscillations. So what do is you time for 10 oscillations. And once you finish 10 oscillations, you stop, and that is for 10 oscillations. So suppose I get 11.90, 11.95, 12.02. Just write it down. Those are the three timings you're getting for this length, 3 trials for 10 oscillations. So how do you do it? You oscillate, you fix the 30.7 centimeters, and then you oscillate it. Time it. Let go. 10 oscillations. And after you finish 10 oscillations, stop the stopwatch, write it down. Continue for the same length. Another 10 oscillations. You go the next time. Make sense?
Yes, sir.
Now, how do you time it? How do you get the timing? How do you do the timing? A common mistake from students is this. The best place to do the timing is when it crosses the
Expo marker.
middle position, like this point, not here. Because if you're doing the timing from the end, you'll be a little more relaxed in starting and stopping the stopwatch. Because, you see, it literally stops here. So it waits more time at this point than at this point. Right? Yeah. So if you want to do the timing, the best place to do the timing is at this point, the middle. So look at me doing the timing. If I start the stopwatch, I'm starting it at this point. So this is where I start the stopwatch. Then it goes and comes back, and that's when it finishes one oscillation. But often I see students timing like this. So they start the stopwatch by calling out 1, 2, 3. What is the mistake there? They're calling as 1 when they start the stopwatch when it is not even done an oscillation yet. So the best thing to do is when you start the stopwatch, always call out as 0. So when you start the stopwatch, 0, 1, 2, 3, and then 9, and then 10. That's when it finishes actually 10 oscillations. Does it make sense? So you always start the stopwatch calling out 0, not 1. And always do the timing from the middle because it spends the least time there. So you are forced to start and start the stopwatch very promptly. Make sense? And the timing should come pretty close. Look at this. This is pretty close. If it is coming like this, that means you're doing a good job. If it is like spread out a lot, that means your starting and stopping is terrible. Okay, so you have to kind of repeat it until you get very consistent timing. What comes next is average time. Average time, and you know how to do the average. Add all this and divide by 3. And so the average here comes out 11.96. So average is coming out 11.96. Right? It'll be 11.95666666. So you put it down. Now keep the significant figures correct. When you're measuring with a meter stick, since it is measuring up to a millimeter, you need 3 sig figs. Since you're measuring with the stopwatch, it has 4 sig figs here. Keep the same 4 sig figs here. Don't write 11.95666666. Is that clear? And then the next step is going to be time period. And what is time period? It is the time taken for one oscillation. So what do? You divide this with 10. And so your answer is 1.196. Don't round it because you need 4 sig figs. keep the number of sig figs. Just because you're dividing by 10 should not change the number of sig figs of your value. And the last step is to square the time, because we are looking for time square. Look at this equation. We need length and we need time square to investigate it correctly. So the last column is time square. What's time square? Square of this. I mean, square that, you have to round it to the 4 sig figs again. So 1.196 square is 1.4 something something. How much is that? Rounded to 4 sig figs, how much is it? $1.196 square.
1.43 0.
1.430 sounds right. So that is how you write it down. Only 4 sig figs. 1.430. Now what do? After you finish this exercise for this length, increase the length to another. Now when I say increase, don't increase it like minimally. From 0.3, like 30.7 to 31.7 will be like only that much of a change, which will not change this too much. So the best way to change it is, this is in 30s, next one should be in 40s, next one should be in 50s, next one should be in 60s, and next one should be in 70s. So your first length should be in the 30s, somewhere around the 30s. So suspend it, and what would be the length? Take it down. The next time you pull it down till here. Once you suspend the meter stick, suspend the pendulum, you put this meter stick and check. Now if it comes 41.5, you write it as 0.415 here. You don't have to make it exactly 0.4. Make sense? Make sense? You don't have to keep adjusting the length to make it exactly 0.5, 0.6, 0.7. It's unnecessary. Whatever comes, write it down. You're going to do this for five different lengths, and you repeat the same thing. And finally, you will have 5 different lengths and 5 different time squares. Is this clear so far?
Yes.
And after you do this, that's when you plot a graph. What are we trying to investigate? Length and time square. And what do you know about the length and time square? They should go hand in hand. Look at this equation. What is g? Is it a constant?
Yes.
4 pi square is a constant?
Yes.
That means length and time square should go hand in hand, which means if length is double, time square has to double, so that it will be a constant. So length and time square should be proportional. Length is proportional to time square, which means if you plot a graph of length and time square, you're expecting a what line? If something is proportional, linear, straight line. That's what you're expecting. So we plot a graph. And on the graph you have the y-axis and the x-axis. What we're going to plot on the y-axis is length in meters. And what you're going to plot on the x-axis is time square in second square. I'll show you how to plot a graph later. I'll show you how to plot a graph, and that's very important. Right, so we have length here and time square here. If you plot those values over here, you will get points. As you can see here, the points are all going from the 0. Which means, according to this equation, when length is 0, your time square is supposed to be kind of 0. It's supposed to be. So you're expected to have a graph starting from the origin. It's supposed to start from the origin, but it may not start from the origin. Why? Why it may not start from the origin is because when you're doing the experiment, there are 2 kinds of errors.
Why?
There are two kinds of errors when you do an experiment. One is called random error. And what's a random error? This is a random error. Sometimes your time is lower than this. Sometimes it is higher than this. That's called random error. Sometimes, it all depends on how good you are at time. Sometimes your times are high, sometimes your times are low. That's called random error. And the consequence of random error is this, the scatteredness of this, the points are scattered. That clearly shows there is random error. If the points are scattered, shows more random error is present. If the points are almost straight, that means you've done a good job in timing. Then there's another one called systematic error. What is a systematic error? A systematic error is an error that's coming into all your measurements the same way. Like what? Like the length of the pendulum. What did I say the pendulum's length is? From the point of suspension to
Center of gravity.
center of gravity. But instead, you always measure from the bottom. Or instead, you measure only the string's length, not the pendulum at all. And you're doing that regularly. So all these numbers are wrong. And they're all wrong one way. Make sense? The consequence of that is the graph will shift from here to either here or here. And that is called systematic error. If there is no systematic error, the graph should pass through origin, which means no y-intercept. If there is systematic error, you will see a y-intercept. You will see a y-intercept. So the purpose of drawing the graph is to get rid of random errors and systematic errors. How do you get rid of random errors? Draw the best fit line. Draw the best fit line. That will get rid of random errors because you're trying to take an average, right? That's how you get rid of random errors. And how do you get rid of systematic errors? Because you see, it is not hitting origin. It is hitting somewhere. So there is a systematic error. But the systematic error is removed by taking the slope. Because when you take the slope, you're only looking for the change in length here and the change in the time square here. Change. So if you're making a mistake of this length and you subtract it, the change is gone. I mean, like when you do the change, the error is gone. Make sense? No?
Yes.
Error is gone. Like if I stand on a scale today, it weighs 180 kilograms, 180 pounds. So, okay, it shows a number 180. Is that my weight?
Yeah.
Is that what I'm weighing?
No.
Look at the jacket and belt and shoes. So that's not my weight. That's wrong. 180 is wrong. Now I come tomorrow and stand on the same scale. It shows 181. Is that my real weight?
No.
No, that's also wrong. But how much did I gain?
No.
1 pound? Is that correct?
Yes.
That is correct.
Isn't it?
So both the readings are wrong, but the change is correct. Is that understood?
Yes.
Yeah. So the same thing here. This length is wrong, but the change in length is correct. So when you take the slope of this line, and what is slope? Rise over run. That's a slope. Rise over run. And so when you take the slope, you are getting rid of what error? Systematic error. Just understand this. By drawing the best fit line, you're getting rid of random errors. By taking the slope, you're getting rid of systematic errors. That's the very reason why we actually plot graphs for investigating experiments. And once you've done this, can you see this? Slope is what? Length over time square. Isn't this the slope? So your ultimate equation is 4 pi square times slope. So this is your ultimate equation. So in the formula used, you should put this one too. This is what you're actually going to do in the end. So the only calculation you're going to do is this. The only calculation in this experiment that you're going to do is this, which is 4 pi square times that number. Is that clear? Good. Now, Procedure, you know what to do, right? Write down everything that you've done. What comes after procedure is observation, which is this. And what comes after observation? Calculations. You should write all these things down, if you have forgotten the order. Calculations. What is going to be done in calculations? The first thing that you're going to put in calculations is this graph. Insert the graph. You put the graph on your Word document. That's your first job. And then you do this calculation, which is the only calculation you're going to do in there. After calculation, what comes next? Precautions. So what kind of precautions are you going to take during this experiment? You can say so many things. One of the most important precautions is this.
Measuring from middle.
First precaution is this. What is the time period equation? Time period T is 2 pi radical L over G. That equation is correct only for small angle oscillation, like 5 degrees, 10 degrees. This much. That equation is not valid for this oscillation. It is not valid. So while doing the experiment, I'll keep reminding you, keep the amplitude of the oscillation small. You don't need to do this. You just do small angles only. That's one of the
Why
precautions.
doesn't the equation work for large?
Because this equation is derived by assuming that you're not swinging too much. Like there is a small angle approximation that is done, and the small angle approximation is
Pi is 2 pi.
no, I'll tell you what it is. Like the value of sine theta
Yeah.
and tan theta will be very close only for small angles. You can check it out. What is sine theta? Sine 5 degrees. How much is sine 5 degrees?
Hold on, I think I may be great.
Sine 5 degrees?
0.087.
0.087 something. Now tan 5 degrees?
Same thing.
Almost the same thing?
Yeah.
That is why that's called small angle approximation, and that we are using in this derivation. That's why when you're deriving that equation, since we are taking small angle approximations into account, you are not expected to do this. Clear?
Yes, sir.
Okay. So a small angle is only this much, 5 to 10 degrees. That's enough. Because for 10 oscillations, this will sustain. This will go on for 10, 20, 30 oscillations. So you should be good there. That's one of the precautions. Next precaution is make sure you measure the length from the point of suspension to the center of gravity. And next one is make sure the timing is done as promptly as possible.
How do we find the center of gravity?
Because it's a sphere, it'll be the center of the sphere. Then other precautions that you can actually say is small angles, and then measurement of length properly to the center of gravity, and measurement of time, precise measurement of time, not precise, accurate measurement of time, all that. So precautions, and then after that the last thing is conclusion, where you say, all right, this is what I got. I found the gravity to be 9.8 or 9.9 or whatever meters per second squared. That's your final answer.
And that's all we have to put in there.
In the conclusion,
Just
you put that there, and then after that you have to say your opinion about this lab, like how did this lab go, and what do you understood about the lab, and your impression about the lab. That's what you should write in the conclusion. So this is what the lab is. But I know you are familiar with everything except the graph now. You know how to make a table, right?
Mm-hmm.
The only thing is the graph. So I'm going to show you how to plot the graph. Is it all good? I can take this out. Can Can you turn off those the switch next to the door? Okay.
Schultz did it.
I only have one team.
Hmm?
Did I have only have one team?
I use the restroom.
The green tea.
Not right now.
Dave's gonna go cheat the spit.
It's got a mix stuff on it.
I will.
Whoa! Alright, so the first thing you need,
No one.
Not
the
funny.
first thing you need is Excel. Make sure that you have a computer with Excel in it. Now if you don't have a computer with Excel in it, no excuses, you have to find one which has the Excel, or go use a computer from the library, or use your parents' computer, or
Is Google Sheets banned?
No, it's tea stuff.
some features may not work on that. So let me show you how to do this. All right, first thing I need to do is open Excel.
It's 400 lose.
I know.
Yeah. Some of you might have used Excel, some of you might not have used Excel, but I'm showing you how it is done. So, Excel, you have, these are the rows, 1, 2, 3, 4, they are numbered, and these are the columns, which are A, B, C, D, F, G, H. And as you go more in order, it will become 2 letters and 3 letters and all that. What you need to now do on Excel to plot a graph is this. Enter the X variables of the graph right there. Pay attention. Enter the X variables of the graph here. I should have used it. So in column A, enter the X variables. What are the X variables on our graph?
It's Times Square.
Times square. So whatever be the times square values that you have on your table, you're going to put it here. So I'm going to throw some numbers. 1, 2, 3, 4, 5. These are just random numbers I'm throwing, for example. So this is, what are these numbers? This is your times square values on the last column, right? The column B is where you put your Y variables. What is the Y variable on your graph? Length. So I'm going to put some length over here, 2.1. I'm just throwing some random numbers here. 3.8, 6.3, 7.9, 10.3. All right. So what are these numbers that I put here? It is just to replicate, the length, which is the Y variable. So these are the Y variables, these are the X variables. Simple so far?
Yes, sir.
Now what you do after this is select these cells like this. Up. Just select these cells, only those cells. Select it. After you select it, click Insert. And after you click Insert, go down here to what is called Charts. And click that. And when you click that, you will get multiple charts
What is it called?
available. One is a scatter alone, without any dot, without any lines. Then scatter with curves, scatter without any points, and stuff like this. So you see all these different kind of graphs that can be plotted. What we are looking for is the first one. The first one is scatter. Click on that. Your graph is there.
That's so cheeky.
And look at this graph. Can you see the random error that is there?
Yeah.
It doesn't look to be a straight line, so there is a random error. And obviously there could be a systematic error. So what do you do from here on? Pay attention, because this is exactly the same pattern that you're going to use for all the kind of labs that you do, not only for this class, for maybe the next year, and maybe in universities. You may have to use this tool. So just learn it properly. When you come to this point, there are two ways of going forward. one method of going forward is right click on any of these markers. Right click on any of those markers. This is one way of doing it. And when you right click on any of these markers, there's something called add trend line. Click on that. And when you add trend line, it draws the best fit line for you. So you don't have to worry about anything. And it does the best job. So it drew the best fit line. And it's asking you, what kind of line are you anticipating to find? Of course, it's a linear graph. So you're looking to get a straight line graph. And then scroll all the way to the bottom. And it says here, display equation on chart. Click on that. And there is your equation.
That's a slope.
And what's the slope by looking at that equation?
2.05.
Why is that 0.07?
So
Not at all.
let me increase the size of this, then you'll actually be able to see better. All right, that is our equation. So you see the equation is y equal to mx plus b format. So m is a slope which is 2.05. So that's what you're looking for, the slope. What is this negative 0.07?
Why?
That is a y-intercept. What is it? Why is it there?
Is it, if it's below 0, does that mean the origin goes through 0 first? Or no?
No, it means it's going to hit somewhere here. It's going to hit somewhere here at the bottom. Right? So it's going to hit at the bottom here. So this negative 0.07 tells you the presence of systematic errors. But we don't care because we're going to take the slope very soon. So pay attention now.
Yeah.
Right now? Oh yeah, we got the slope already. So this is an equation. We got the slope. So your graph is almost fine. And I'll show you this once again. You can do it the way I showed you just now. Or you can go and click this plus sign. And then it actually tells you a trend line option. Click on the trend line. And then go to this thing. And then choose linear. And then after that, go to more options. And then you will open up this. And then go down and click on display equation on chart. So that is a lot of work. Right? I think the right clicking option is faster. So different computers are different. So you can actually like do it any way you want. Do you understand this so far?
Yes, sir.
Perfect. Now what is missing on this graph is it doesn't detail anything. So chart title. Okay, so click on chart title and type the value, type the chart title, which is in this case simple pendulum. That's your chart title. And what else is missing right now?
The
There are
time square
labels for
stuff like
Yeah.
the X and Y
Like
axis.
it doesn't say what your axes are. So we need some labels for that. And to get those labels, there are different ways of getting it. One way of getting it is go to chart design and then click add chart elements and you'll see all those things there. Or the other way of doing it, if you see this plus sign, then it's much easier. Click on the plus sign, click chart axis titles, and you can see those two axis titles have appeared. So now I'm going to type in what this axis title is. It's supposed to be time period squared. And in what unit it is? It is
Second square.
in second square. There it is. So I've got that done. Similarly, you click on this and then type in length. In what? Meters. Done. Is it clear so far?
Yeah.
So far clear?
Yes, sir.
Okay. Now what you do is we need to transport this graph from here to your Word document where you're making your lab report under calculations. So click on an empty, right click on an empty space on the graph, like this, here, 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 right click there, and then it will help you to copy. So now you copied the graph. And then next thing what you do is open up your Word document where you're actually typing your lab. So you're typing your lab here.
Oh,
See how fast I type.
Wait.
that was sick.
See if you read what the book.
So That is where I'm doing the calculation. So this is my calculations area, and I want to insert the graph there. And how do you insert the graph that you copied?
Control V.
Control V, and the graph is there.
That's
Yeah.
And you can resize the graph, and you can even add extra stuff. Look at this. I can add more grid lines to make the graph look like a graph.
that's so.
Look at this. All you have to do is insert it here. Did you understand how to make a graph on Excel
Yes, sir.
and how to get the slope
Yep.
and how to transport it to Word document?
So we don't even
Simple
have to find
thing.
a slope.
It can't be easier. Now, which one do you
Defines the
prefer?
slope for you.
On paper or on Excel?
Excel.
Definitely Excel is so good. And it is always more accurate because the computer is helping you to draw the best fit line. You're not doing it yourself.
I've learned a lot today, just for seeing him.
And then after this, what do you do?
You don't
After
care.
this, you do the calculations for
He does care.
g equal to 4 pi squared times the slope. So in this case, it will be g equal to 4 pi squared times 2.05. Make sense?
Yeah.
And then you finish it off with precautions and calculations, precautions and conclusions. Any questions on drawing the
I'm so
graph?
prepared for this one.
Yeah, thanks. This is-
All good? You understand how to do Excel,
Yeah.
and you have to do how to do this thing.
For materials, do you want us to like put pictures in of the
Bro.
materials?
Oh yeah. No pictures.
No, but you need a picture in the theory, which is a pendulum's picture.
Alright.
You can actually take an actual picture of what you're doing, or you can actually what I drew is
I'm
enough.
gonna take a picture. of
What I drew is enough. You can just draw that. So you can actually draw a pendulum just like this.
Don't forget your computer.
You can just draw a pendulum by just using shapes
When do we get out of here?
like this.
Oh!
And then
Oh yeah.
there you go.